Good morning. Welcome back to the course. In this lecture, I'll talk about design for environment. We have talked about the algorithms, analysis of variance, and I have talked about the quality function deployment and value engineering in the previous lectures. So, I'll take this course forward while discussing design for environment in this lecture. So, the contents are: first we will see what is the need of design for environment, then we will see the sources of waste, then we will see how to implement the DFE, design for environment. Then we will see what is life cycle assessment, which is essentially one of the techniques to conduct or to implement design for environment. Design for environment, I can say, is an apt tool or methodology that acts as an umbrella under which various methodologies like lean manufacturing, green manufacturing, life cycle assessment is an essential part here. These things comes into play. So, what is design for environment? Product design for environment is a design approach for reducing the impact of products on the environment. This is something understood. The definition what it says: the products can have adverse impact on the environment through polluting processes and the consumption of large quantities of raw materials. So, the impact can be adverse also due to consumption of large amounts of energy and difficulties in disposal. So, as I said, it is material, energy and disposal, or I could say pollution. So, because of this, the manufacturing concerns have to consider the product's entire life from the creation of the product to the final disposal. So, in this life cycle, there are many events of creating pollution, maybe recycling, remanufacturing, reusing, reducing waste, refusing to use some of the unnecessary functions or the processes. So, these things would come into play. Now, product design for environment is a contemporary topic because people are talking about the green manufacturing products, and also we will discuss the life cycle assessment. Life cycle assessment is the term that came later after life cycle analysis. LCA was first called LCA, but that is life cycle analysis. Now, it is known as life cycle assessment, which involves life cycle inventory analysis or inventory management tools. Many other tools have come into play, that is complete assessment. Earlier it was just the life cycle analysis. So, we will discuss various software tools also, the online tools, those are available, and the offline tools which are free versions, and some purchase versions are also there. Several researchers all over the world are busy attempting to design products that minimize the impact on environment. Why is it so? We have discussed that there is a need to mitigate the environmental effects of manufacturing. I will actually show you illustration here that is given by OECD, Organization for Economic Cooperation and Development. So, they say that greenhouse gas emissions will double by 2050 if we do not act. If you see, this is a prediction, okay, or the future forecast. It is going in this direction. At 2050 it has stopped. So, what is this going? Would it just go parallel like this, or would it go something like this? Let us try to see this, that where are we moving to. For this, I would like you to see this video that is given by Professor Al Bartlett, who is no more. He was a pioneer professor who in 1969 gave a very celebrated talk on the arithmetic, population and energy. He used the mathematical tools or calculations to show that how population is increasing and what are the resources that are available now and where we are leading to. So, let us see this video. I would have actually shown this video well in the start of the course itself, but let us see this video to have a feel that where are we moving to and what is the need of design for environment.
Well, it's a real pleasure to be here and to have a chance just to meet with you and talk about some of the problems that we're facing. Now, some of these problems are local, some are national, some are global, but they're all tied together. They're tied together with arithmetic, and the arithmetic isn't very difficult. Now, what I hope to do is I hope to be able to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So you say, well, what's the exponential function? This is a mathematical function that you would write down if you're going to describe the size of anything that was growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about, it's ordinary steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now that longer time is called a doubling time. We need to know how you calculate the doubling time, and it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. So our example of 5% per year, you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Well, you might ask, where did the 70 come from? The answer is it's approximately 100 multiplied by the natural logarithm of 2. If you wanted the time to triple, you'd use the natural logarithm of 3. So it's all very logical. But you don't have to remember where it came from if you'll just remember 70. Now, I wish we could get every person to make this mental calculation every time we see a percent growth rate of anything in a news story. For example, if you saw a story that said things have been growing 7% per year for several recent years, you wouldn't bat an eyelash. But when you see a headline that says crime has doubled in a decade, you say, my heavens, what's happening? Well, what is happening? 7% growth per year. Divide the 7 into 70, the doubling time is 10 years. But notice, if you're going to write a headline, you never write crime growing 7% per year because most people wouldn't know what it really means. Now, do you know what 7% really means? Let's take another example from Colorado. The cost of an all-day lift ticket to ski at Vail has been growing about 7% per year ever since Vail first opened in 1963, and at that time you paid $5 for an all-day lift ticket. Now, what's the doubling time for 7% growth? 10 years. So what was the cost 10 years later in 1973? 10 years later in 1983? 10 years later in 1993? And what do we have to look forward to? Now, this is what 7% means. Most people don't have a clue. Well, let's look at a generic graph of something that's growing steadily. After one doubling time, the growing quantity is up to twice its initial size. 2 doubling times, it's up to 4 times its initial size. Then it goes to 8, 16, 32, 64, 128, 256, 512. In just 10 doubling times, it's 1,000 times larger than when it started. And you can see, if you tried to make a graph of that on ordinary graph paper, the graph will go right through the ceiling. Now let me give you an example to show the enormous numbers you get with just a modest number of doublings. Legend has it that the game of chess was invented by a mathematician who worked for a king. The king was very pleased. He said, I want to reward you. And the mathematician said, my needs are modest. Please take my new chessboard and on the first square place 1 grain of wheat. On the next square double the 1 to make 2. On the next square double the 2 to make 4. Just keep doubling till you've doubled for every square. That will be an adequate payment. Well, we can guess the king thought, this foolish man. I was ready to give him a real reward. All he asked for is just a few grains of wheat. Well, let's see what's involved in this. We note there are 8 grains on the 4th square. Now I can get this number 8 by multiplying 3 2's together. It's 2 times 2 times 2. It's 1 2 less than the number of the square. Now that follows in each case. So on the last square, I'd find the number of grains by multiplying 63 2's together. Now let's look at the way the totals build up. When we have 1 grain on the first square, the total on the board is 1. We add 2 grains, that makes a total 3. We put on 4 grains, now the total is 7. 7 is a grain less than 8. It's a grain less than 3 2's multiplied together. 15 is a grain less than 4 2's multiplied together. Well, that continues in each case. So when we're done, the total number of grains will be 1 grain less than the number I get multiplying 64 2's together. And my question is, how much wheat is that? You know, would that be a nice pile here in the studio? Would it fill the building? Would it cover the county to a depth of 2 meters? How much wheat are we talking about? The answer is it's roughly 400 times the 1990 worldwide harvest of wheat. Now that could be more wheat than humans have harvested in the entire history of the earth. And you say, how'd you get such a big number? Well, it was simple. We just started with 1 grain, but we let the number grow steadily till it had doubled a mere 63 times. There's something else that's very important. The growth in any doubling time is greater than the total of all of the preceding growth. For example, when we put 8 grains on the fourth square, the 8 is larger than the total of 7 that were already there. When we put 32 grains on the sixth square, the 32 is larger than the total of 31 that were already there. Every time the growing quantity doubles, it takes more than all that you'd used in all of the preceding growth. Now, let's translate that into the energy crisis. Here's an ad from the year 1975, and it asks the question, could America run out of electricity? America depends on electricity. Our need for electricity actually doubles every 10 or 12 years. That's an accurate reflection of a very long history of steady growth of the electric industry in this country, growth at a rate of around 7% per year, which goes with doubling every 10 years. Now, with all that history of growth, they expected the growth would just go on forever. Fortunately, it stopped. Not because anyone understood the arithmetic, it stopped for other reasons. But let's ask, what if? Suppose the growth had continued. Then we would see here the thing that we just saw on the chessboard. In the 10 years following the appearance of this ad, in that decade, the amount of electrical energy that we would have consumed in this country would have been greater than the total of all of the electrical energy we had ever consumed in the entire preceding history of the steady growth of that industry in this country. Now, did you realize that anything as completely acceptable as 7% growth per year could give such an incredible consequence that in just 10 years you'd use more than the total of all that had been used in all of preceding history? Well, that's exactly what President Carter was referring to in his famous speech on energy. One of his statements was this. He said, and in each of those decades, more oil was consumed than in all of mankind's previous history. Now, by itself, that's a stunning statement. Now you can understand it. The President was telling us a simple consequence of the arithmetic of 7% growth each year in world oil consumption, and that was the historic figure up until the 1970s. Now there's another beautiful consequence of this arithmetic. If you take 70 years as a period of time, and note that that's roughly one human lifetime, then any percent growth continued steadily for 70 years gives you an overall increase by a factor that's very easy to calculate. For example, 4% per year, you find the factor by multiplying 4 2's together. It's a factor of 16. Now, a few years ago, one of the newspapers here in Boulder quizzed the 9 members of the Boulder City Council and asked them, what rate of growth of Boulder's population do you think it would be good to have in the coming years? Now, the 9 members of the Boulder City Council gave answers ranging from a low of 1% per year. Now, that happens to match the present rate of growth of the population of the United States. We are not at zero population growth. Right now, the number of Americans is increasing by more than 3 million people every year. No member of the City Council said Boulder should grow less rapidly than the United States is growing. Now, the highest answer any council member gave was 5% per year. Well, you know, I felt compelled. I had to write him a letter and say, did you know that 5% growth for just 70, I can remember when 70 years used to seem like an awful long time. It doesn't seem so long now. Well, that means Boulder's population would increase by a factor of 32. That is where today we have one overloaded sewer treatment plant. In 70 years, we need 32 overloaded sewer treatment plants. Now, did you realize that anything as completely all-American as 5% growth per year could give such an incredible consequence in such a modest period of time? Our city council people had zero understanding of this very simple arithmetic. Here's an interesting headline from Los Angeles. That headline probably has something to do with this headline. So, well, how are we doing in Colorado? The Denver Post tells us that we're the growth capital of the USA and proud of it. The Rocky Mountain News tells us to expect another 1 million people in the Front Range in the next 20 years. But in the Post, there was an interesting story. Someone was quoted as saying, Colorado has a 3% growth rate. That's like a third world country with no birth control. We send foreign aid, family planning assistance to countries that have smaller population growth rates than Colorado has. Well, as you can imagine, growth control is very controversial. And I treasure the letter from which these quotations are taken. Now, this letter was written to me by a leading citizen of this community. He's a leading proponent of controlled growth. Now, controlled growth just means growth. This man writes, I take no exception to your arguments regarding exponential growth. I don't believe the exponential argument is valid at the local level. So you see, arithmetic doesn't hold in Boulder. Now I have to admit, that man has a degree from the University of Colorado. It's not a degree in mathematics, in science, or in engineering. Let's look now at what happens when we have this kind of steady growth in a finite environment. Bacteria grow by doubling, and one bacterium divides to become 2, the 2 divide to become 4, the 4 become 8, 16, and so on. Suppose we had bacteria that doubled in number this way every minute. Suppose we put one of these bacteria in an empty bottle at 11 in the morning and then observe that the bottle's full at 12 noon. Now there's our case of just ordinary, steady growth. It has a doubling time of 1 minute. It's in the finite environment of one bottle. I want to ask you 3 questions. Number 1, at what time was the bottle half full? Well, would you believe 11:59, 1 minute before 12, because they double in number every minute. And the second question, if you were an average bacterium in that bottle, at what time would you first realize that you were running out of space? Now think about this. This kind of steady growth is the centerpiece of the national economy and of the entire global economy. Think about it. Well, let's just look at the last minutes in the bottle. At 12 noon, it's full. 1 minute before, it's half full. 2 minutes before, it's a quarter full, then an eighth and a 16th. Let me ask you, at 5 minutes before 12, when the bottle's only 3% full and is 97% open space just yearning for development, how many of you would realize there was a problem? Now, in the ongoing controversy over growth in Boulder, someone wrote to the newspaper some years ago and said, look, there isn't any problem with population growth in Boulder because, the writer said, we have 15 times as much open space as we've already used. So let me ask you, what time was it in Boulder when the open space was 15 times the amount of space we'd already used? And the answer is it was 4 minutes before 12 in Boulder Valley. Well, suppose that at 2 minutes before 12, some of the bacteria realize that they're running out of space, so they launch a great search for new bottles. And they search offshore, on the outer continental shelf, in the overthrust belt, and in the Arctic. and they find 3 new bottles. Now that is a colossal discovery. That discovery is 3 times the amount of resource they ever knew about before. They now have 4 bottles. Before the discovery, there was only 1. Now surely, this will give them a sustainable society, won't it? Well, you know what the third question is. How long can the growth continue as a result of this magnificent discovery? Well, let's look at the score. At 12 noon, 1 bottle's filled. There are 3 to go. 12:01, 2 bottles are filled. There are 2 to go. And at 12:02, all 4 are filled, and that's the end of the line. Now, you don't need any more arithmetic than this to evaluate the absolutely contradictory statements we've all heard and read from experts who tell us in one breath we can go on increasing our rates of consumption of fossil fuels. In the next breath they say, but don't worry, we'll always be able to make the discoveries of new resources that we need to meet the requirements of that growth. Well, some years ago in Washington, our Energy Secretary observed that in the energy crisis, we have a classic case of exponential growth against a finite source. So let's look at some of these finite sources. From the work of the late Dr. M. King Hubbert, we have here his semi-logarithmic plot of world oil production. The line's been approximately straight for over 100 years, clear up here to the year 1970. Average growth rate, very close to 7% per year. So it's logical to ask, well, how much longer could that 7% continue? Well, that's answered by the numbers in this table. In the top line, the numbers tell us that in the year 1973, world oil production was 20 billion barrels. The total production in all of history, including that 20, was 300 billion. The remaining reserves, 1,700 billion. Now, those are data. The rest of this table is just calculated out. Assume that the historic 7% growth continued steadily each year following 1973, exactly as it had been for the preceding 100 years. Now, in fact, the growth stopped. Not because of the arithmetic, it stopped because OPEC raised their oil prices. So we're asking, what if? Suppose the growth had continued. Let's go back to the year 1981. By 1981, on the 7% curve, the total usage in all of history would add up to 500 billion barrels, the remaining reserves 1,500 billion. The reserves at that point are 3 times the total of all that have been used in all of history. That's an enormous reserve. But what time is it when the remaining reserve is 3 times the total of all you've used in all of history? And the answer is 2 minutes before 12. Well, we know for 7% growth, the doubling time is 10 years. We go from 1981 to 1991. By 1991, on the 7% curve, the total usage in all of history would add up to 1,000 billion barrels. There'd be 1,000 billion left. At that point, the remaining oil would be equal in quantity to the total of all that we had used in something like 130 years of the oil industry on this earth. By most measures, you'd say that is an enormous remaining reserve. But what time is it when the remaining reserve is equal to all that you've used in all of history? And the answer is it's 1 minute before 12. So we go 1 more decade to the turn of the century. That's like right now. That's when 7% would finish using up the oil reserves of the earth. Now let's look at this in a very nice graphical way. Suppose the area of this tiny rectangle represents all the oil we used on this earth before 1940. Then in the decade of the 40s, we used this much. That's equal to the total of all that have been used in all of history. In the decade of the 50s, we used this much. That's equal to the total of all that have been used in all of history. In the decade of the 60s, we used this much. And again, that's equal to the total of all the preceding usage. Now, here we see graphically what President Carter told us. Now, if that 7% had continued through the 70s, 80s, and 90s, there's what we need. But that's all the oil there is. Now, there's a widely held belief that if you throw enough money at holes in the ground, oil is sure to come up. Well, there will be discoveries in new oil. There may be major discoveries, but look, we have to discover this much new oil if we would have that 7% growth continue 10 more years. Well, ask yourself, what do you think is the chance that oil discovered after the close of our class today will be in an amount equal to the total of all that we've known about in all of history? and then realize if all that new oil could be found, that would be sufficient to let the historic 7% growth continue 10 more years.
This was Professor Al Bartlett, who was a pioneer professor. He died in 2013. He was an alma mater of Colgate University and Harvard University, and he worked in University of Colorado Boulder, where he developed the research in these lines. Now we have a little feel that what is the impact of not considering the environmental issues these days. So let us try to come back to the stages of product life cycle. This we have discussed before, the stages of product life cycle that Professor Deepu Phil have discussed. The product life cycle goes like this, the sales are here, the time goes like this, the product is introduced to market, then growth, maturity, decline. This is something I am not going to consider in this lecture. The product life cycle that I am telling is the other viewpoint from the extraction of the ore to the final use of the product and then disposal of the product. So if you remember, we had discussions on before use, during use and after use. I am talking about that product life cycle in this lecture, not this one, not this one. So in this product life cycle, to meet the challenge of the design for environment, the designer must understand the process of life cycle assessment, LCA, that adopts a total view by analyzing the entire life cycle of a product, process, package, material or handling activity. So life cycle stages encompass these 6 stages. Number 1 is extraction and processing of raw material. Here processing means manufacturing also. Okay. So raw material extraction is number 1. If I need to put in 2 factors here, factor A and factor B in part 1, then transportation and distribution, then use, reuse and maintenance, then recycling and composting, then final disposition. Now, what is extraction? The products that you use. For instance, you use a car. The car is having multiple materials in it. It has aluminum, it composites, plastics, polymers, rubber, various kinds of materials are there. Those are extracted from some source before. It is extraction of ore. Please be mindful, I am talking about the extraction of ore. That means the very initiation of the product from the ground, the ore is extracted, then it is treated to make it usable, then the metals are extracted from that or the materials are extracted, then comes processing. Processing is, that is manufacturing that we are all talking about. This part B is processing. But when we are talking about product life cycle, after processing also what happens? We have to package the product. Packaging, then for instance you buy a car, you go to a showroom to select a car, those are transported there from the manufacturing unit, that transportation. Okay. Then distribution to different units, then is use, used by the first owner, used by the second owner, reuse, then maintenance, the average maintenance cost and inputs, those are coming, there are inputs in maintenance as well, those are coming. So that maintenance. Then when we try to completely dispose the car, so when the car has worked for its operating period, then we try to send the car to the dismantling section. Now what does this dismantling section do? They do recycling, then composting, then final disposal. These things happen. If I put these stages here, first is raw material extraction. Okay. Second is raw material processing. Third is manufacturing. Then comes assembly and packaging. After this, transportation, right. After use, what happens? One finally eliminates the product. I would say product elimination. So these are the major stages: raw material extraction, raw material processing, then is manufacturing, then assembly, then transportation, then use and product elimination. So it goes in this direction. I would like to show you how reuse, recycle, remanufacturing work, and from where it can be connected again. For what can be reused here at material processing stage, what can be reused at material extraction stage, and what can be reused at manufacturing stage itself. So these things let us discuss. So what happens? These are the stages from where the disposal come here. This is actually disposal, which is the final resort if nothing can be done. But before disposal, what we can do? Okay, let me put three words here. We can recycle, recycling, remanufacturing, and reuse, right. What happens? Reuse is one when uses the product, one person eliminates the product and other person can reuse this product, like I took the example of the car. This again becomes a use for the new person. So this is one cycle, it is moving in this direction. So it is moving in this clockwise direction, it is coming from here and going here. This is reuse. So the first resort that design for environment discuss is reuse. If not reusable, then we can remanufacture, that is maintenance and repair, all those things. So even this product elimination can come here, remanufacturing. So where does this remanufacturing go? After remanufacturing, the product can be again reused. This is actually the flow, the secondary flow of the product. In red color I am showing the primary flow. This is primary flow, I would put here. This is secondary flow, and in the red color we have primary flow. Here these arrows. Okay. Now the secondary flow can further come to the recycling stage. From product elimination it can even come to recycling stage here. Components, those are recycled. For instance, some of the components aluminum can be again melted and casted into new forms. In remanufacturing what happens? Remanufacturing is overhauling of the engine, the denting and painting and all those things. Those comes in remanufacturing to make the product reusable again, that comes here. If that is not possible, then recycling can happen. Recycling is aluminum, plastics, all those components are taken about and they can be used for some other purposes. So that is recycling. So that goes here to the manufacturing process again, right. This is recycling. Now recycling can also go, some of the parts can also go to raw material reprocessing. Like I said, aluminum can be casted and can be rebuilt or reshaped into a different form. There are different grades of aluminum. The body aluminum is different, the aluminum that is used for the pistons, that is different grades of duralumin, all those materials are there. So this is the secondary flow. In between we have here is waste. Waste comes here like this. I will put maroon color for waste. Waste is that comes to disposal, waste comes from all the stages, from all these stages waste could come, from raw material, processing, there comes waste here, okay, from this direction, this direction, this direction. When we are reusing or remanufacturing, here also the waste comes here, in this direction waste comes, and in this direction waste comes. So, this is the final disposal. I will put it in a black box. This is the disposal that should be avoided. As far as possible. However, any product has a operating life and it has to finally disposed of. We are only trying to enhance this life as far as possible. The final aim has to be actually waste free manufacturing or waste free manufacturing processes and resource recovery. This is an illustration that is adapted from the work done by Fratila in 2013. You can read the complete paper if you like. So, the goal of reuse, recycling, remanufacturing, that is emerged with the innovative engineering materials, manufacturing processes and systems which are aiming to provide multiple life cycle products. So, we are trying to have the multiple life cycles. If I try to put it here, this is one circle, this is second circle, this is third circle, this is again fourth circle, that is going from this direction again of raw material. So, this is 1, 2, 3, 4. So, we are trying to produce multiple life cycles than just one. One is just purchasing the product like extraction of ore, then manufacturing, transportation, etc., using, disposal, that is all. No, this is only one life cycle. Let us try to reuse, remanufacture, recycle and try to have multiple life cycles here. So, this is the ultimate aim of this discussion. The need of ecological efficiency and the environmental concerns are often associated with the production of minimum waste. Minimum waste means minimum toxic emissions. Toxic emissions into air, soil, water, any of these emissions are to be avoided, and minimum consumption of energy. So, these all are to be aimed at. So, what we can do in reuse? So, reuse is nothing but using the product again and again, and so it is the change of the owner, or we reuse the product in some different way, like the paper that we are printing. The one side of the paper is plain, and if those paper are not usable, the second side can be used again, that is reused, and then that can be used to recycle finally if the both sizes are printed and then they are not required anymore. So, that is reuse in some different way, or reusing of towels or cotton clothes to mop the floor. So, this is all examples of reusing. So, recycle in traditional sense is where you might spend your oil for fuels blending and it is recycled as a fuel, or maybe you send your fluorescent light electronics into facility where it is dismantled and the parts are recycled separately. However, other wastes that are not hazardous wastes that also have the ability to be recycled. These are a few recycle examples. Then remanufacture is nothing that is just maintaining or working on the product to bring it in the usable form. The finally product has to be disposed. Here disposal, before disposal we can recycle, and before this we can remanufacture. before this we can reuse, and also before this we can reducing the production, and this is how the sustainability or greenness that rises in this direction. And also one can even refuse, that is diffusing is limiting your needs, but that is not the thing. People are demanding more and more products with more and more facilities, so these things are coming into play. So this is how greenness goes like this. These are the typical stages of product life cycle and the product life cycle orbits. So what is the importance of design for environment? So when we talk about design for environment, so if I talk about the manufacturing alone, how does that happen? We have the CAD model before, or we have design here. Okay, after design in manufacturing we have the preliminary analysis. Right, then we have the conceptual design. After conceptual design we have preliminary design. After preliminary design is passed, we have detailed design, and then we have final manufacturing. Right. So this is the flow of the manufacturing. We make a design, or the CAD would actually go here. This is just the idea, okay, to correct myself. So, idea is there, the preliminary analysis is there, whether the idea is possible or feasible or not. Then we go for CAD or conceptual design. What is the conceptual design? Then we make the preliminary design. This is just the initial CAD, the overall concept of the model in this stage 3. This is 1, 2, 3. In stage 4 we have the preliminary design, and we then try to see what are the various changes required. Then we make a detailed design which had all the blueprints, etc. Then we go for manufacturing. So, where essentially the design for manufacturing has to work like value engineering, as we discussed, it has to start from very beginning. So, this is pollution prevention. Pollution prevention, and pollution prevention is maximum if we conduct DFE here, and it is minimum if we conduct DFE here. So, design for environment is considering the environmental impacts in the design stage itself. So, this is the line for, or I would put a green line here. So, this is DFE, and if we do not conduct DFE, the other way is end of pipe treatment, that is this in this direction. Okay, this is end of pipe treatment. In between, in the previous session we discussed in value engineering, this is the concluding point, but in between also it can be something like this. This is something like this. So, this is actually a small room for pollution prevention, right. In green color we have DFE, and in black color we have end of pipe treatment. End of pipe treatment, that is manufacturing has happened and now we are doing it, end of pipe or end of pipe treatment. This is forced air. Okay, that has to be done because the design is not good. We have to work for the environment. So, the pollution rises in this direction. So, this is minimum, this is maximum, this is minimum and this is maximum here in this direction. Here we have idea, preliminary analysis, CAD, conceptual design, preliminary design and final manufacturing. Has we get here, actually here we get the final product, and in the preliminary design or in the detailed design we can also have a prototype. These days this is known as rapid prototyping. So, this is importance of DFE. With this, I would like to have a break here and we will continue the design for environment in the next lecture, where I will discuss the importance of DFE. Further few lines on this would be discussed. Then we will see what are the sources of waste. Then we will go to our life cycle assessment. Thank you.